Okay, let's get going. Hope you guys enjoyed your spring break. I hope I didn't disappoint anybody by sending your midterm exams yesterday morning. Sorry, the timing might not have been the best. We'll talk about the midterms a little bit in a second. If you didn't get an email from me, let me know. There's a website where you can download your mid-year exam. So if you haven't gotten that yet, let me know, and I'll get you that email, or I'll get you the website address for that. The mid-year, it's out of 78 points, not 86. I'll talk about that in a few minutes as well. Let's see. All right, so here's what we're going to actually do today. So we'll talk a little bit about the Unix tip of the day, which is going to be on zip, which happens to be a program that's built into Unix that you can use to zip up your files, just like any other zip file. Then I'll talk a little bit about the midterm comments. I'm not sure if most of you didn't know about this or just ignored it, but there were mid-semester reviews that you could do online. Only like 22 people in the whole class did them. So I will talk about them. I think the people that did them had some pretty critical comments, which were good, and we'll talk about those. But I'm not going to make sweeping changes because 10% of the class. I'm not sure that necessarily means that you all think the same way, but we'll get to that. And then we will talk about heaps, which is the next data structure that we're going to actually get into. Any questions before we actually get going? No? OK. Let's see. The Unix tip of the day. So I thought I'd show you an easy way to actually compress your files so that you can mail them to yourself. On Wednesday, what I'm going to do is I'm actually going to show you how to use the built-in email client to actually email your programs to yourself instead of using the other methods that we've already talked about. So let's see. Let's say that I have a folder here, and it's got a bunch of files in it, right? And I want to send those to myself. Now, we already talked about how to get them from your computer using SCP or some program that you download that drag and drop. You can do that. Or if you go into the prior directory, so let's say I do cd ... which means go to the one higher in the directory stream, OK? And then I do zip. I say zip-r for recursive. What it means is it goes into all the folders that you're going to give it in a second and then zips all the files in there. And then lab5.zip and then lab5. What it will do is it will actually take all those files and store them in your zip file, which is now ls star.zip. It's called lab5.zip. And then you can actually email it to yourself or SCP it to yourself as one big file. So kind of nice. You can actually do unzip as well. Unzip lab5.zip, and it will try to replace the ones I've already got there, but it will unzip them as well. So pretty straightforward stuff. And like I said, on Wednesday, I'll show you how to use the built-in mail thing to actually send emails to yourself through the terminal. Kind of cool. Questions on the Unix tip of the day? Yes?
When you zip something,
yep.
when you zip the files, do they disappear?
They do not disappear. So they're still in Lab 5. If you want, you've got a copy of them now in the zip file, so you could delete that Lab 5 folder, rm-r lab 5, and it would go boop, but now they're gone. Right? And then if you do unzip Lab 5, it'll actually put them back right where they were before. So it's a good way to store up all your stuff, especially like at the end of the semester. If you just want to be like, I just want an archived copy, or I want to email it to myself in case I ever want to look at it again, remember the font days of Comp 15, then you can do that. OK? Other questions on that? All right. OK, so let's see. So Unix tip of the day. All right. Anybody a Redditor here? I found this on Reddit the other day. Our midterm class average is 22%. We were hoping to speak to the professor. If you can't see this, this says, everyone go away. Basically, some professor did not want to discuss the exam. I am perfectly happy discussing the exam with you guys. The exam, let's see. Here's what the overall grades were. This is not percentages. These are out of 78 points. OK, so this is what it looked like. On Wednesday, I'll plan on going over some of the specific questions. I've still got a couple people who need to kind of make up some parts of the exam. And I'm going to make it different enough that it's different, but the same enough so I can compare it to you guys and whatever. Anyway, so I don't want to go over that today, but I will go over the some of the questions on Wednesday. If you do have some specific questions, please feel free to email me or stop by office hours. We can certainly discuss. If the grading was wrong, if the grading was incorrect, email me and I'll fix it. So I mean, if there's an issue with grading, or well, we'll discuss if we disagree on whether it should be graded that way. But point is, if we made a mistake on grading, we'll certainly fix it. Yeah.
So I got 68 out of 84. Does that mean if it's out of 78, it's 68 out of 78?
Yes, it does mean it's 68 out of 78, which hopefully will be happy for everybody, right? Yeah, on the page, if like the one on the thing, it said out of 84. I think I fixed it at this point. I don't know if anybody's looked at it this afternoon, but if you go back and click on it, you can actually see the whole PDF. And on the PDF, it should say out of 78. But either way, it's going to be out of 78. What happened was the 5 points were for the bonus. If you got the 5 points right, then that was 5 extra points. And then I gave everybody an extra bonus point because I screwed up grading one problem. So I just gave everybody that extra point. OK? So but if you have any other questions, let me know. All right. On the bonus, a couple people emailed me and said, hey, what's the answer to this one? And I said, figure it out. Like for the one that was like the power. And that person in particular happened to figure it out. So there you go. OK. Anyway, we'll go over more of the exam on Wednesday. Any other questions on the exam? No? Yeah.
This is kind of like a syllabus, like let me go over that for you kind of question. But like for the test percentage on syllabus is like 2%, right?
Yeah, good question. Very good question. So here's what. So before I answer that question in particular, so I would say anybody who did in this range, I'm pleased. Okay, I mean, I think if you're in the lower end of this range, probably, there are a couple things you might want to do a little better. If you're in this range, not as good, obviously. But if you are in this range and you do much better on the final, I will count the final more, like for you. Okay, so don't, like if you had a bad day or whatever, we'll work that out kind of on an ad hoc basis. If you did like in this range, you're doing great and you don't have to worry about that, and you can't bomb the final and still do it, but you know what I mean. I will count the one that means that you did better out if you did significantly better. That said, I don't remember exactly what the percentages are. It's like 10% or something like that. It's not for the midterm. It's not a huge amount. Obviously, we give midterms so that we can see how you guys are doing, but it's not a huge amount on that. Yeah, Margaret.
Well, I believe the syllabus says collectively the final and the midterm are 30%.
Yeah, I think collectively it's 30%. I mean, 20 and 10 sounds about right for the final versus the midyear. But at the same time, I'm going to be somewhat lenient in the sense that if you had a bad day, I'm not going to count that against you in the overall picture. So hopefully that's fair enough. Okay. Any other questions on the midyear? No? Okay. So let's see. So as I said, there were about 22 responses out of like 180 people in this for the mid-semester feedback. There are mixed reviews about the class. I mean, I'd say some were very nice reviews and said good things about the class. Others were relatively critical. We'll talk about the critical ones up here. And there are things that I can do better to make this a better class. So I will attempt to do that over the next however many weeks we have left, 5 weeks or 6 weeks or whatever we have. Let's see. So here's one of the comments. Lectures don't align with the programming assignments. So I got a bunch of these comments that kind of said sort of the same thing. Look, I was already familiar with dynamic arrays. We should have benefited more from assignments on stacks or queues. They are coming. Like we are getting some more assignments that will be a little more based on newer data structures. So don't stress too much about that. It's a fair comment, though. And I'll work on better assignments as far as that goes. Let's see. A bunch of people said, look, we need to be required to write more code. This is a tricky one, because on the one hand, I agree. Having you guys write more code for assignments probably gives you more practice on this stuff. I agree. It's also, remember, there's 184 people in here, and there's a lot of differentiation between people's abilities and such. And so if I just said, go ahead and write, start from scratch, that would harm a lot of people. Although some of the future assignments, and we're only going to have probably 2 more assignments, they're going to be more coding from scratch. So you will get that. Practice. Nothing is stopping you from writing your own code, though. So don't, if you want to get more practice on writing this stuff, feel free, and I would be happy to talk to anybody about kinds of projects you can be working on your own as well. Let's see. I think let's see. Provide does not go up. Yeah, we're working on that. This is another fair comment. Provide doesn't go up necessarily until like the day of the homework being due. Please don't rely on that, though. I mean, I hate to say we could just make provide go up at like, the day of and then not have any tests. But we try to give you some tests, but not, you're supposed to be writing your own tests as well. But fair enough comment, we'll work on that. This one was the one, did not pull any punches on this one. Assignments are poorly designed and thought out, have been disappointingly fill in the blank and artificial. When you're a teacher, you have to take these criticisms, in stride, I suppose. But so as far as like the fill in the blank and artificial part, I understand that is causing some consternation for some people. The problem is kind of twofold here. First of all, we're in school, and school just tends to have artificial kind of assignments in general. I mean, unfortunately, that's kind of the way it goes. I mean, we come up with these assignments, and are they real stuff that you'll use the rest of your life? Probably not. The fill in the blank part, we're working on that, so I do hear that. Assignments don't seem to have much relation to what we're learning in class. Okay, I mean, I guess I understand that. I think the labs, there were some comments about the labs too. I think the labs hopefully are a little more relevant to the most recent stuff. Like today, for instance, you'll do a lab that's on heaps, which is what we're going to talk about today. Okay, and then I don't feel the assignments we've been given have done so much to help us understand the material. Well, I apologize for that. I mean, I hope the assignments, we will work better on getting better assignments that will help you learn a little better on that. Okay, let's see. More comments. Make the labs simpler. This is another tricky one. So the labs are, you've only got 75 minutes. We have to make the labs such that you can understand what's going on, and you can actually do some work that's actually legitimately working on the stuff we've talked about in class. I understand some of the labs, like that maze lab, that was a little tough to get everything that was going on behind the scenes to do the maze lab. Fair enough. But again, it's tough to do that in 75 minutes. So we'll work on it, though. There are a couple others here. I feel like the labs are very difficult to finish. Hopefully, your lab instructor, I've mentioned this before, if you don't finish the lab, you are not going to get penalized on your lab grade. That is not the point of the labs. I mean, I want you to finish them if you can, but I'd rather you dig in and try to do the best you can on working on them so that you get them, you get something out of the understanding the data structures. Okay, for what it's worth. So don't worry about not finishing the lab and affecting your grade, because that is not what's going to happen. Post solutions, I can't do that. I probably should have been doing that. I can do that. And then pre-make code as little as possible. Again, this is a tough one. If I don't pre-make the code, all of a sudden you're like, I don't know how to build a heap, and then 75 minutes goes by and you're still not even having any idea. So I'm not sure I can quite help that one too much, but we'll see what we can do. Let's see. Unify the lecture and labs assignments more. I'm not sure I necessarily agree that the labs aren't as unified. The assignments, yes, again, I get it. I'll work on unifying those a little bit more. And then, let's see. Homeworks are not what we do in class. All right, I get it. we'll work on that. Okay, harder to understand the concepts when we have little or no practice with them. I get that. I think we've been trying to test some specific things, and some people weren't thrilled with what we were testing. Okay, but again, 22 of you. I don't know. I mean, and 10 of them were the ones that were these critical. And then finally, let's see. Please make the course more difficult. Again, it's tough. On the one hand, I would love to make the class more difficult, to give you bigger, broader problems. On the other hand, there's a lot of different people in here, right? So it's a tough challenge. Make a start project from scratch. You will be starting some projects much closer to scratch, if not directly from scratch, coming up. And don't cover as many specifics in class. That one's a tough one. I'm not sure I know what that one really means. And by the way, feel free to email me for real or email me anonymously with any of these concerns. And we can have a dialogue anonymously too, just so you know. And then finally, I would suggest the teacher post links to things that should be read prior to class. Good suggestion. I'm probably going to post more things. I will start posting things, at least at the end of the lectures, that you can go look and find more information about. Yeah, question?
You had a fairly serious leak.
Oh no, you do have a serious leak over there. Yeah, there's a leak in the ceiling. Well, how about this? Does anybody want to volunteer to go and talk to the biology department and just say there's a leak down here?
Can we just call facilities?
Yeah, do you know the facilities number?
Yeah.
If you got it, call them. And then I would maybe move so the ceiling doesn't fall in on you. I would move over here. If it falls in, there's an exit here. There's an exit there. Well, I think Allie's going to call the thing.
We're really tight over
At facilities? Thanks, Allie. Yeah, I might even move a couple steps over from that one. That's kind of funny. All right. Yes?
When are we going to get the second question?
Yeah, this, oh boy. We're working on it. Yes, we're probably going to have it graded, I want to say, by the end of the week. I apologize for that one. There's not as much I can do specifically about it, but yes, we'll get that one done. And as far as I can tell, you guys did very well on it. So I know you guys worked hard on it. So that's good. There was another hand up here, maybe? No? OK. Any other comments on either the mid-year or wait, there might be another. Nope. Any other comments on the feedback? If you have more feedback, critical or not, I am certainly willing to take it and have a discussion about it. So yeah, Jason.
An idea about making the class difficult.
Yeah.
In terms of doing that student class, would there be opportunities for extra credit?
Extra credit. Let me think about it. I don't know exactly how that would work so that everybody could kind of benefit from it. You know what I mean? I mean, look, if you don't want to do extra credit, don't do it. Sometimes that works, sometimes it doesn't. It's also hard to deal with 184 people in that mentality, but I'll think about it. Good idea. Any other comments about that stuff? OK. Oh, the ceiling. Oh, no, it didn't stop leaking. No. OK, anything else? All right. All right. Let's go on to what we're going to do today, which is, so remember, when we try to remember back before spring break, I know it was a long time ago, we talked about these things called priority queues. Now, a priority queue, okay, is an abstract data type. In other words, remember what priority queues were. Priority queues were lists of items, okay, that are based on, that have some key. Thanks, Allie. Did you get in touch with them? They say they come down? OK. That are based on some key where you can order the keys. And the keys can drag along other information. Okay? And that's what a priority queue is. And remember, there's three things you can do with priority queues. You can request the minimum element, you can insert an element, or you can remove an element. Right? And that's it. And that's the data type. Okay? Now we've talked about a couple ways of actually building a data structure that is a priority queue. We talked about two of them before, an ordered list and an unordered list. And remember, we had some trade-offs, right? For an unordered list, you could insert items instantly, because all you had to do is stick them right at the end of this list. So like if it was an array, you stick the item there, and it's done, right? And that takes one operation, more or less, and it's order one. But then when you wanted to search through an unordered list, you had to look through every single element to make sure that you found the minimum. And that took on order n. And then remove was the same way. First you had to find it, and then you had to actually remove it. So order n. Then we decided, oh, let's do it this way. Let's keep an ordered list of items. Great. Well, the problem with that was, not the problem, but one of the trade-offs was, for an ordered list, you have to keep the order when you're inserting it, which takes time. You have to figure out where it goes, then you have to move all the other elements and plop it right down there. And again, you have to look through all the elements to do that. Okay? But minimum elements right at the end, remove min, right at the end, you just remove it. Very easy. So those are the trade-offs for the building a priority queue out of lists or arrays. Okay? Well, it turns out there's other data structures we can use. Some people said, hey, why don't we build a priority queue out of a binary tree or a binary search tree? We could totally do that, right? If we had a binary search tree that was like, let's say it was, I don't know, 7 and 3 and 10 and 9 and 12, let's see, and 2 and then 1, right? That's a binary search tree. And you could build a priority queue out of that. We would, if we wanted to find the minimum, we know how to find minimum, right? We'd go all the way to the left and then return that value. If we want to insert, we know how to insert into a binary tree. We know how to remove from a binary tree. So we could have a priority queue built from a binary tree. No worries, right? What would the worst case asymptotic behavior be for find min? Order n. Not perfect, right? We're still dealing with order n's. What's but the average case? Probably order log n. So maybe it's better than these, but not perfect, and so on and so forth. Well, there is another type of data structure that we're going to talk about today. It's a brand new one. Okay, it happens to be called a heap. All right, a heap is another tree-based data structure, okay? And it satisfies what we call the heap property, which is very simple. It's much like the binary search tree property, except that it's different in the following way. All it says is that parents have to have a higher priority key than any of their children. Okay? In other words, if this is we've got trees that are minimum trees or maximum trees. If we have the following like numbers here, right? I wrote down a bunch of numbers over here. And what we can do is we can build a heap such that this actually makes sense. We're going to say in this case that 1 is the minimum, is the highest priority, kind of like what we did before. Right? We could do 1, and then we could do 6, and then 14. OK, 6 and 14 are both lower priority than 1. So they can go in their children like that. All right, and then we have 7 and 9. And I'll do it this way. 7 and then 9. And then 16, 40, 16, 40, and 22. All right. That is what we call a heap. All right, notice it's different from a binary search tree in that, right, well, the left doesn't necessarily have to be bigger than or smaller than the root. In fact, it's got to be greater than the root. They both do. But this order doesn't matter. There is no ordering between siblings like this. OK, 6 and 14 could be swapped just as easily, right, as long as the rest of the tree, or as long as the rest of the heap made sense. OK, so that's what a heap is in that's what the heap property is. Anybody notice how I built this tree? I did this one, then 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 this one. What does that mean that this tree is at this point? Anybody know? It's called a, there we go, complete tree. Yeah, this is a complete binary tree because all the elements are in order. The only time you don't have a full level is at the end, and it's from left to right. So it's filled left to right. The next one will go here, right? And the next one will go here. Okay? So that's what a heap is. Pretty straightforward. There are a couple different types of heaps. By the way, we're talking about binary heaps. You could have heaps that have more than 2 children, but we're going to only talk about binary ones for now. Okay? You've got min heaps, which is the minimum values on the top, and you've got max heaps where the maximum values on the top. Okay? And all of its children and each subtree are less than the tree. You can also have, like in lab today, we'll do binary heaps where these are actually string values. Like there's a string there and a string there and a string there. But you can compare strings. You just do it alphabetically, right? And it turns out if you do string 1, like if string 1 is less than string 2, that actually comes out and it says if it's true if string 1 is alphabetically before string 2. Okay, so you can compare them that way. All right. Questions on what heaps are at this point? Complete trees, complete binary trees with all the elements in each subtree being a lower priority than their parent. Easy enough. Yes?
When you say min and max, you mean minimum priority and maximum priority?
I don't mean minimum priority and maximum priority. Good question. What I mean is, in this case, the highest priority is the lowest number for a min tree. For a max tree, the highest priority is a high number. OK, that's the difference. Yeah, this one is still the highest priority. The root is always the highest priority in this case. Yeah, Margaret?
So heaps always have to be complete trees.
Okay, heaps have to be complete trees. We'll see why in a minute. Yeah, Allison? And then.
So you have the highest priority as the root. Is that because, or I guess I don't understand why you do that. Because if you like want to access the highest priority thing, which I think is what you'd like generally want
You
to
do? Yeah.
Why would you make it just root?
What's the well, good question. If it's the root, don't we normally keep a pointer, either a pointer to the root or it's the beginning of like I think, right? So if I want the minimum, it's right there. And access time is instant. You don't need to search through it, which is great. Yeah. Susanna.
What would be like a practical application of a priority queue program?
Wow, good question. What's a practical application of a priority queue program? So let's say, boy, practical one. Let's say you wanted to, well, I gave some examples before about like with the airline reservation system, right? Like who gets priority when they come into the airline? You know, it types into the computer who's got priority to go in first class. Well, it has to do with, you know, that, so you'd want to prioritize it that way. Anytime you can think of either alphabetizing as a priority type thing, but anytime you can compare two values and you want to compare a bunch of values, you can turn it into a priority queue. It's also very good for sorting, which we'll find out about a little bit about later. Yeah, Jane.
Didn't you say like the emergency room was a good example?
Emergency room's a great example. Now, that's not necessarily a program, although maybe they do that. I don't know. I don't know. This guy's bleeding out his head, high priority. I mean, boop, you know, and a little number pops up. I don't know. But yeah, I mean, there are real examples, but we do use priority queues a lot for sorting. We use them a lot for ordering things in general, which is generally sorting. OK, good. Yeah.
If you wanted to insert like a specific number into the heap, seems like in some cases you would have to like rearrange them.
Yeah, that's a very good question. You're like 2 minutes ahead. We're going to talk about the operations and how we're going to insert into heaps and do all the other priority queue operations. Very good point. But we'll get to it. You can brainstorm that in a sec. OK, anything else? All right. OK, number one, remember, there's no implied ordering here. OK, no implied ordering. By the way, one thing I never really talked about before, in a binary search tree, I don't know if you figured this out. When you do the in-order traversal of a binary search tree, you actually print it out in sorted order. This isn't going to work for this one, but remember how in-order traversal went? You go to your left, print, and then go to your right. So go left, 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 no left to go, print, come back up, print, go right. It turns out it does it, for a binary search tree, it does it in increasing order, which is kind of nice. Gives you a nice way to sort a binary search tree. But anyway, back to heaps. Heaps, no implied ordering. Okay? All right. We've said that heaps are completely full. A lot of times you'll see it written like this, right, where you've got the tree with all the numbers in it. And these ones are just like the empty nodes here. They're not actually filled. Most of the time we leave empty nodes off. It's nice to see them in a heap because you kind of get the feel for where they are and which one you have to fill next and so forth. Okay? Internal nodes are left of external nodes. Internal nodes are the ones that actually exist in this case. So internal nodes are always to the left of the ones that don't exist. Okay? All right, this is an important property of a heap. OK, so before we saw that we can store binary trees in arrays. I call them vectors here. That just means array, right? We can store these in arrays. And we can also do that with a heap. OK, we can sort a binary tree in an array or a heap. In this case, notice something. Element number 1 is in position number 1, right? And you're going to yell at me, and you're going to say, hey, look, you've told us all along that we always index things by 0, and why all of a sudden are you jumping to 1? And turns out the math is just a little easier. I'll show you that in a minute. But what we're going to do is put the root at 1, and then its 2 children are going to be at the next one, and then their 2 children are going to be at the next 2, well, next 4, et cetera. OK, remember how we did this for binary trees? OK. One thing you might ask, you might say, well, look, doesn't that mean you're wasting a little bit of space? Yeah, you're wasting space. It's not that much normally. It's 1 node, right? What's nice is that we normally deal with powers of 2, OK? And in powers of 2, in this case, there are 16 elements. What's the maximum number of elements we can have here in this part of the tree here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Nice. It does fit in our 16 element thing. OK? So you guys here for the ceiling. Did he say he was coming back? Oh, OK. OK, nice. Hopefully it's not like raw biological like craziness from the biology department. Hopefully, yeah, really. All right. So anyway, so the point is that we can put these in here. The reason we do this with heaps is because this makes it really fast to access these things. And I'll show you that in a sec. OK. With this ordering here, OK, here's what we've got. The left child, your left child, if you are at position I, is always at I times 2, right, or 2 times I. So if you are at 8, right, or if 8 is here at position 3, well, then its left child has to be at position 6, 14. Is 8's left child 14? It is, right? Its right child is always 2i plus 1, right? So 2i plus 1 is 7. 13 is the right child of 8. Okay? One of the nice things about doing it this way is multiplying by 2 for computers is really, really fast, as it turns out. Okay? Anybody know how a computer multiplies by 2 or by 4 or by 8? Ethan, go. It puts a 0 at the beginning. Yes, I know what you mean, but let me draw it out for you like this. OK. Remember how we counted in binary a couple weeks ago? 1, 0 is what in binary? It's actually 2 in binary, right? If it was just a 1, it would be 1. And then the 1, 0 is 2. OK, 1, 0 is 2. 1, 0, 0 is 4. 1, 0, 0, 0 is 8. 1, 0, 0, 0, 0, right, with 4 zeros is 16. If you add another 0 on there, you get 2 times the amount. So that's actually pretty easy for the computer to do. What the computer really does, anybody want to, somebody who said it earlier? No? I thought I heard it. I'm sorry? Bit shifting. Yeah, they do what's called shifting. So let's watch this. If this is a 1, let's say we had a bunch of zeros here. This is 2, right? All you need to do to turn this into 4 is to shift everybody over by 1. Right? This 0 goes here, this one goes here, this one goes here, this 1 goes here, and this 0 goes here, and you put another 0 there, and you've now multiplied by 4. It is really, really fast for a computer to do that. So multiplying by a power of 2, really fast. We've changed this now, so all you have to do to find the left child is multiplying by 2. What else might be easy? Adding 1 is also very easy, so that's good. In terms of dividing or multiplying, dividing by 2 is exactly the same. Dividing by 2, shift over by 1 the other direction. Right? It's so easy. In fact, division is normally a very hard operation, because you guys have all done long division, right? It's like it's hard to, you got to figure out how many times it goes in, blah, blah, blah. It's a big, long process for non-integers. For integers, dividing by 2, so simple. Just shift. Right? So when we see that the parent of somebody is at I divided by 2, and these little guys mean the floor function, which means do an integer division, right? So if you are at position 6, right? Well, we want to find the parent of 14. 6 divided by 2 is 3. So the parent of 14 should be at 8. And look, it is. Parent of 14 is at 8. Nice. The parent of 13, well, 7 divided by 2 is also 3 in integer math. And that's also the parent of 13. Okay? If you have the shifting, and this is like advanced, right? This is the advanced stuff. That number in binary happens to be what? You may remember? This is, by the way, this is 2 to the 0, 2 to the 1, 2 to the 2. It's exactly like 2 to the 3. 2 to the 0 times 1 is 1. 2 to the 2 times 1 is 4. 4 plus 1 is 5. So this is 5. 5 divided by 2, right, is 2. Well, when you do it in integer division, but how do you do that? You shift everybody over. That means it's going to become like this. And see how I just shifted over? The 1 goes away, and it ends up being 2. So it's actually really fast. Okay? So if you're wondering why we do this and why we actually make it over to 1, part of it is because it's just faster, and the math is easier, and it just makes more sense. Okay? Questions on that? Good. You will deal with lots of this stuff in Comp 40 if you end up taking it, like binary kind of bit shifting and all that. It's fun stuff, says the nerdy professor. I like it. I think it's good stuff. All right, questions on that? OK. All right. Now, here's where we get into the actual priority queue operations. There were 3 of them. We had to know how to do the minimum. We had to know how to insert. And we had to know how to remove the minimum. OK? Doing remove min and insert and min element, when you do min element, you're just returning. You're not actually changing the heap at all. OK? Insert or remove actually does change the heap. So let's talk about this. Before we go into I have a couple slides on it. Let's just figure out how we might do this. OK, let's brainstorm some ideas. OK, idea number 1. How do we do min element? Allison already brought it up earlier. I think it was you, or maybe it was Margaret. Who was it that said? It was you. Yeah. what do we do to return the minimum? Return the root, which is at what position? It's at index 1. So if we have a heap called h, and we want the minimum, we return h of 1. Right? What's the order of that? What's the asymptotic behavior of that? Constant, right? It takes one operation. Boom, you're done. All right, so that's actually pretty nice. Okay, it's nice to be able to do that and say, we've got that great benefit of a heap. OK, let's go into the other ones, which are a little more interesting, much more interesting. Insert item. OK, in order to insert into this heap, what are some ideas of how we might do that? How about some ideas about how we might go ahead and insert into this heap? And we could pick any value. Let's say I wanted to insert, let's see what's not in there, 8. If I want to insert 8, what do I have to do? What are some ideas about what to do for this? Those of you who just took the lab, you're not allowed. Yeah. Charlie says, look, put it at the next available spot. You mean here? OK. So if I put it right there, is this still a heap? Actually is, isn't it? OK. That was a bad example for this one. Although that was a good idea. Let's say I wanted to insert 2, and I did the same thing. Is that now a binary, a actual heap? It's not, it doesn't follow the heap property. So we've broken the heap property. OK. Where else could I have put it that might have made just as much sense as at the end? At the beginning. We could have replaced 1 with 2, right? And then we got to figure out where to put 1. Problem is, let's say we've got to figure out where to put 1. And then that's just another problem altogether. If we inserted 0, well, then that would be fine. But then still we have to put 1. I mean, the only time, like if we insert 2 and we put it there, and we displace 1, well, 1 is still supposed to be there. So that doesn't really help us. But we have put the 2 here. Where does this 2 actually need to be in this case? Yeah, it has to be up here somewhere, right? It doesn't really have to be over here anywhere. Yeah, it does have to be kind of a child of 1 in the case that it has to be smaller than this one and smaller than this one and so on. So could you think of a way to start this process of getting 2 where it needs to be? Yeah, Susie. Would you replace it for the larger child of where? You mean like either this one or this one? No, I meant like 14. Like 14 or here. Well, what if it was something where it was actually still smaller than this or this? Or rather bigger than that for that. Then that might not work. But I like that idea. I like that idea. Think back to some of the operations that we know are really fast, right? Finding a child is fast. Finding a parent is fast. So right here, what's the only thing this thing really knows about is its parents, right? It has no children. But this does know about its parents. Its parent, I should say. Yeah. Yeah, swap with your parent if you need to. That make sense? I think that makes sense. I like that idea. In this case, swap with your parent if you need to. Is 2 a higher priority than 7? It is, so let's swap it. All right. 2 and 7. Are we done yet? Start thinking recursively, because we're not done yet, and we've now got to do, same sort of thing to this one. What's this one need? What happens to happen to this one? Swaps with its parent, because 6 is lower priority than 2. 2, 6. Does it ever need to check any of its children? As it turns out, it doesn't need to check its children at all. Okay, why doesn't it need to check its children? Well, let's say we're looking at, let's go back to, see if I can do this. That was 7 and 6 and 2. OK, is there a case that if this is somehow smaller than this, but also smaller than this? No, there's really no way for, or rather bigger than this, I guess, right? Because this has to, by definition, be bigger than this, right? So that means that if this is smaller than this, it also has to be smaller than this one. So So there's never a reason you need to go back and check any other children. Okay? So here we go. 2, 6, and 7. We swap the 2 and the 7. We swap the 2 and the 6. And that ends up there. And we're done. This process is called either bubbling up, because it kind of looks like it goes bloop, 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 and bubbles up, right? Or it's called upheaping. In other words, you're moving something up the heap. Okay? So that's what we can do with this. And Charlie's absolutely right. You put you place it in the position the next free position, okay? Which, by the way, is at heap size plus 1, because we started with 1, 2, 3, 4, 5, 6, 7, 8, and that 8th position. In this case, it's not going to, well, in this case, it was right here, right? And that 8 happens to be 22, interesting. And that 8th position, right, was the last one in here. And so the next one is the heap size plus 1. You can always put it at heap size plus 1. And then you do this bubbling up. And the bubbling up is as simple as checking with your parent. If you're a higher priority than your parent, swap. And then recursively do that on your parent. Done. Fair enough? That's bubbling up, or upheaping. OK. How about remove min? Now we've got something that's a little more interesting. We want to actually remove the minimum. We know how to find the minimum, right? It's easy. If we want to remove it, we're going to actually return it. So like, let's say 1 goes out here, and we're going to return that, right? What happens to this one? Ideas. What are some ideas of what we could do at that point? Yeah? Take the last element and replace the root with that one. That's not a bad idea. And then what? And then bubble it down. Somebody's been either reading ahead or knows this stuff already. That's very good. So I like that. I like that idea. Let's hold on that for 1 sec. Are there any other ideas? Yeah?
I would just compare it to the smaller child and swap it with that and do that recursively.
That's a very good question. Now, if we compared it with our smaller child, like which one? The one you mean? Or just whichever the smaller child is, put the smaller child here?
Yeah.
OK.
And then do that for the child you swapped.
And then do that for the child you swapped. So 2 would go here, and then 6 would go here, et cetera.
Yeah, and then 7 would go.
And then 7 would go there. And then, yeah, well, OK. So what is I like that idea. What's the problem with that idea? Anybody know? There is a problem with that, unfortunately. Let's see, this was 6 and 2, and there. Well, yeah. There you go. You might not end up with a complete tree. What if it was on this side? Right? If the 2 and the 14 were swapped, you'd make this one go here. Very good. You'd make this one go here, and then maybe this one go here. And then all of a sudden, you've got this blank space, which means it's not a complete tree. So that's the only issue. It happened to work on this one, but it wouldn't always work. Yeah?
What if you take the smallest of from the bottom row, and then you put that, and then you recursively check to see
The smallest of the bottom row? Same issue, really. If you take this one, then you need to somehow fill this in, or it's not a complete tree. That's the only problem, right? If we took, let's say this one had been the 7 and this had been the 2, right? Well, we would have ended up moving this one, and now this is an empty space, and you can't have an empty space.
Well, then just maybe move right.
Just move rightmost. That's fine. You could do that, right? But it sounds like more work than a relatively simple idea. Yeah, very good. Yeah.
Well, this is kind of going with my question before. If you knew that you were going to remove the min a lot, like if that was how your priority keys were.
Yeah, which it always is. You always are going to remove the min, yes.
Versus just like looking at, yeah. Why
Yeah.
wouldn't you just construct your tree the opposite way so that you're always just taking the last element?
Why wouldn't you just construct the tree the other way? So yeah, I see what you mean. So you're saying have a heap where the last element is the one that you care about. How would you do insert? I mean, you're right. You'd still have to do that, but then you'd have to somehow figure out how to, like, let's say you inserted it here, but it should be here. Well, then you got to climb back up this way and down this way. That's not really that fun. Like climbing up the tree and down the tree. Then that could go on for a while, right? I like the idea, and in fact, there might be there might be one where you're doing that. But keep in mind, yes, we might need to remove the min a lot, but using the answer we heard a little bit earlier, watch how it's actually not too difficult. Okay? So the answer we had earlier was, take the last one. And this is the one we want to be gone at the end anyway, right? Because we've got one less item in our tree. We want to keep it a complete tree. So this one's going to be gone, right? And then it's still a complete tree as long as I fill in the top one, right? If we put it up here, can we bubble down? Exactly. Can we bubble this down and figure out where it needs to go? What would we do to bubble this one down? Which one would we replace it with? The 2. Yeah, if we replace it with a 14, then we're in trouble because 14 is bigger than 2. We need to replace it with the child which has the higher priority, right? So 2 and 7. Let's see, 7 and 2. And then, that's a 7. And then this one and this, what do we do here? Anything? We need to switch it with the 6, right? So 6 and 7. So this is going to be 7 and 6. And then 7 is a higher priority than 22, and we're done. So it's exactly the same idea, except that it's kind of a little bit like reversed. Okay? Not so bad. I mean, I don't think bubbling down is too tricky, right? Move it up here and bubble it down. It does take a little bit of work, right? And you're definitely going to get something that's relatively high priority because you're moving it all the way up there. But that's the easiest way to do it, as it turns out. Yeah, Margaret.
So is bubbling down going to take more effort because you have to compare it to 2 values, or is bubbling up going to have to compare it to 1?
Is it going to take more? Yeah, it'll take one more operation per. I mean, it's going to take a little bit more. It's going to take a little bit more work. But asymptotically, what's our asymptotic behavior going to be for this? Yeah, it's still going to be log n. You're going to have to make a bunch of comparisons, but you're only going to have to go at maximum the height of the tree, right? You're only going to have to go at maximum the height of the tree, which is kind of nice. Okay. By the way, same thing for insert, right? Order log n for insert. Okay, which is kind of nice as well. And for remove, log n. And you see how we've kept the tree as complete, important, and we've regained the heap property of being a proper heap in that sense. Okay? Questions on that? All right. Let's see what we've got here. These are the things we did. Order one operation for min element. That was easy. Return the first element. Well, element at index 1. Insert. We insert at heap size plus 1. That's easy enough. And that probably will disrupt the heap property. Not always, but most of the time. And then you perform this bubble up or up heap. And how do you do that? You compare the element with its parent. And then if it's correct, you don't have to keep going. Like, you don't have to keep going up if it's correct. If not, you have to swap and repeat step 2. You have to recursively do it all the way up. Okay? There is a good animation. This is the animation that we saw before. Let's see. Is it here? Nope. Is it here? There it is. Let's see. Clear. And then, hold on. Slow this down a little bit. There we go. All right. So if we want to insert things, let's insert 5, let's say. Right? It's just going to put it there. And then make this a little bit slower. And then insert, say, 12. And that'll put it at the first empty child. Right? And then insert, say, 7. And let's insert 4. Right? If we insert 4, it's going to go down here, right? Because that's the next free spot. And it's going to start bubbling up, and it actually will make it all the way to the top. Boop. Swap, swap, like that. Okay? And we could keep doing this as long as you want to. Okay? All right. Questions on that? Yeah, James.
So we're talking about an array implementation.
An array implementation of a heap, yes.
So would a linked list implementation just be horrific?
Yeah, a linked list one's going to be tricky, right? A linked list one is going to be tricky. Why is it going to be tricky? Any ideas? You could do it, but it's not quite as easy to find your parent, right? That's the biggest part. And to find your children, that's easy. But to find your parent, unless you have a doubly linked list, which would work fine too. I mean, you could do it that way. It'd be easier to do that. Yeah. But otherwise, we want to do it the array-wise because it's really fast in general. Okay. And remember, this is the data structure. How you implement the data type this is how we implement it in the array. Okay. Any other questions on that? All right. So let's see. We're going to go back here. And, oh, insert. So if we wanted to insert 9 into here, it's going to go next to the 43, right? The left child of 11. Boop. And then we're going to compare it to its parent. And we're going to swap it and then compare it to its parent recursively, swap it, compare it to its parent, and we're done. Easy enough. Okay. All right. Worst case time complexity, order log n. And the average, so this is an interesting one. Inserting has an average complexity, like if you're doing random inserts. Turns out a provably average complexity of order 1, which is actually kind of neat. If you want, you can go look at this paper, which is on, you have to be online in Tufts to actually get access to it, unless you're an IEEE member, which you could be. But you can go here and look. It's from like 1975, and it shows a whole bunch of math to tell you why inserting in the average case is going to be order 1, which, by the way, is a very nice result because we know that it's going to be fast to do inserts into a heap, which is great. One other thing that this paper will show you is that there's a good reason why I'm not making you guys figure out average complexities, right? Because you get published in like journals when you do that. It's hard sometimes, right, to figure out the average complexity. But if you want, if you're a mathy type and want to read this stuff, go right ahead. And it's a good read. It's just kind of intense. So, all right. So that was insert. Then we've got remove, which we talked about. Remove is replace it with the last element to get rid of that last element. Replace the root with the last element. So return the root. And then compare with its children. You have to be careful to check whether the children actually exist, right? Some people who were doing the lab earlier found this was probably the trickiest part of doing the down heap or the bubble down, was figuring out if the child exists. That's not the hard part, but like working out the math for that. How do you know if a child exists? Let's go back for a sec to this one. How do I know if 11 has children? Yeah? Yeah, check and see if, when you say check, what do you mean by check and see if 2 times 5? There you go. If this value is, if 2 times 5 is greater than the heap size, well, we know that that doesn't exist. Right? So if you have the heap size, which you're keeping as you go along, in this case it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 times 2 is 10, which is greater than the heap size. It means that it does not have a left child. If you don't have a left child, can you have a right child? No. So if you check and see if you don't have a left child, then you definitely don't have a right child if you don't have the left. Not the other way around. I mean, you can have a right child but not a left child. Sorry, I lied. It's the exact opposite. The exact opposite. You can have a left child but not a right child. You can't have a right child without a left child. Sorry, said that backwards. Okay? And so that's how you actually go ahead and check these things. But you got to remember to do that. You can't just kind of swap 2 values or check 2 values if one of them doesn't actually exist. Okay? All right. And that's probably the trickiest part about doing the bubble down. Okay? All right. What is the order for bubbling down or for removing? What did we say that was? I don't know if we did. What would the asymptotic behavior be for bubbling down? Log n as well, right? Because you're still only, you might have to do a couple extra operations where you're comparing against both your children. But again, you never have to bubble down farther than the lowest level. Just like bubbling up, you never have to bubble up more than log n of the number of elements. Nice. That's why this is the best. This is why this is the best data structure to use for a priority queue. OK. By the way, I was planning on giving you a heap question on the mid-year, to explain what a heap is and then ask you some things about it and see how you did. But Bruce talked me back from the edge of the cliff on that one. Probably not the best idea to give you new material on the midterm. But sometimes it's fun, but not for you, I don't think. All right. Be careful to check whether children exist. All right. And that's how you do the bubbling down. Okay. Oh, same thing. If we want to remove 5, remove it, replace with 13, and then swap with or do the bubble down until you can't anymore, until there's no more children. Done. All right. And the big O for this we said was log n. All right. So finally, so we talked about the three different types of operations we can do on a heap. What if we want to actually build a heap from scratch? In other words, we have a whole bunch of numbers, 14, 9, 13, 43, 10, 8, 11, 22, and 12, and we want to build a heap. How can we do it? Okay, what are some ideas? Yeah? Yeah, you could just insert each number one at a time. That's not a bad idea. Okay, let's try that. If we just insert the numbers one at a time, let's try it. So 14 goes in. It's the first one in our heap, so that's 14. And then we do insert. We call insert on this with 9, right? And that actually comes in here. That's nice. Doesn't have to do any. Do we have to swap? Yeah, if we're doing a min heap, we do have to swap, right? So we bubble down. Bubble up 9, right? We bubble it up. And it goes 14 and 9. All right, what's next? 13. So 13 goes here. Do we have to do anything to that? Nope. OK, and then 43 goes in here. 43, we don't have to do anything with that. And then 10. 10 goes here. Yes, we do. We swap it with this one. That's going to be 10. And that's going to be 14, right? Et cetera, et cetera. OK, good idea. What's the asymptotic behavior of that? Probably the first time we've seen this one. What is it? N log n. Why is it n log n? You do log n things for each n for n objects. Yeah, I like that. You're going through this, and you have to go through all of these to insert them all. That's n items. Each one of these has the asymptotic behavior of log n for insert. On average, we said it was 0.1, but for this one, the worst case is log n for each one of these, right? N log n, order n log n. OK. Question is, can we do any better than that? Did that not make sense, Sam?
Well, isn't it only log n for the last one?
Is it only log n for the last one? Yeah, that's a good point. For the first, you're right. For the first one, it's going to be log n, but n is going to be only 1, right? Now, you say for the last one. If we have 10 million items here, right? Well, when do you start saying, oh, now I've got about n items total? You know, so it's you got to think big, long term on these sorts of things. Yeah, Lydia?
Would it be if you did just like searching for like the smallest and like next smallest? Is that order n or is that just like order?
Good question. Very good question. So Lydia, correct me if I'm wrong. Lydia's saying, fine, just search for the minimum one and then insert that, and that's going to go right here. And then search for the next minimum one, and that's going to go here, and so on and so on. Well, first of all, we don't need to be that particular. Remember, it doesn't have to be exactly minimum like the whole way. So we're doing a little extra work. But we also, it turns out that doing that, like ordering like that, is n log n on its own, right? So yeah, I mean, you have to go through each one anyway, and then you have to actually find the order. Well, finding like doing the sorting is n log n in general. So yeah, but good idea. Yeah. I like that. So what you're saying is, could you just throw them all in the heap and then do some sort of bubbling to get them in the right place? Why not? I actually like that idea, right? So let's try that. OK? The tricky part is figuring out where you actually have to bubble, maybe. But let's try that. So if we're going to do that, we're going to do 14, and then 9, and then 13, and then 43, and then 10. And that's not a very good circle. And then 8. All right. And then 11. And then 22 and 12. So 22 and then 12. OK. So now, we definitely don't have a heap yet. We've just thrown these into a binary tree. And now we're talking about trying to create a heap from them. Now, what was your idea? To bubble them up, top down? Bubble them down. OK, so you're going to say, take this one and bubble it down. Okay, what goes here then? Like, you mean if I was to take this one and then bubble it down here, remember we had an issue with that in, well, that wasn't too bad actually. We could do that. Yeah, that would work, wouldn't it? Like starting here and then bubbling it down. When do you have to do it for each one? Yeah, you kind of have to do it for every one, which doesn't really help us too much. Like we're kind of doing the same thing. But I like what you're thinking. What if we actually do something slightly different where we say, just go to the first, let's start backwards. Go to the first one that has any children and bubble that one down. That would be this one, right? In this case, this is the first one that has any children, and we're going to bubble it down, right? And that's going to swap with this one. And then we're done with that one, right? Then we go to the next one backwards, right? Because we applied it, we went this one, then this one, then this one, then this one. If we start here and go this one, then bubble this one down, let's try it, right? 43 gets bubbled down. That means 12 goes here, and 43 goes here. Then if we go to this one and bubble it down, what's it going to replace with? Which one? 8, right? So 8 and 13. So this one's going to be 13, and this one's going to be 8. And then how about this one? Do we need to bubble that one down? No, I don't think so. I think we're good. That one's good. And then how about this one? Do we need to bubble it down? Yeah, which one does this switch with? Switches with whichever one's the lowest of its children's priority if we're bubbling down. Or the highest priority, rather. Right? So 14 and 8. Do we need to bubble this one still? Yeah, we do. It's going to swap with 11. 11 and 14. 11 and 14, and we're done. So the question is, how do you find out which one's the middle, or which one's the first one that has any children? What do you think, Margaret?
You could start with what your heap quantity is, and then calculate backwards for which child that is.
Okay, can you do that? Let's think about this. All right, let me put this into an array. Let me just put this into an array here, right? Whoops, maybe need more. All right, so the first one's going to be empty like that. OK, then we're going to put 8, 9, 11, 12, 10. 8, 9, 11, 12, 10. And then 13, 14, 22, 43. 13, 14, 22, 23. OK, 43. Thank you, 43. 43. All right. Now, in this case, what is our heap size? 1, 2, 3, 4, 5, 6, 7, 8, 9. Our heap size is 9. OK. What's the first one that has no children, or that has children? 12, which is heap which one? 4. So we need to somehow go 9 to 4. Yeah? Yeah, that's got to be the first one that has a child, right? The last element has got to have a parent, and that parent has to be the last element's parent. That was kind of circular logic. But point is, so how do you find your parent if you're the last one? Divide by 2. So the heap size divided by 2 always gives you the first one that has children, because it's the child of the last element, or the parent of the last element. Therefore, we can start with this one. We don't have to worry about these guys. Why don't we have to worry about them? Because they definitely don't have any children to worry about. So you go to the first one and then go backwards. And these ones don't either, by the way. So you go this one, and then this one, and this one, and this one. And it actually reduces the amount of time you have to do this. So it's actually a very efficient way of what we call heapifying, okay, making a heap. All right? We talked about this. If we wanted to insert and turn, better way, insert all elements into a binary tree in original order. And then starting from the lowest completely filled level, the first node with children, position n divided by 2, very good, or heap size divided by 2. Down heap each element, also order n to heapify the whole tree. Okay? Turns out it's also order n to heapify the whole tree. So really, it's order n to do the whole thing. Okay. So here's your example of this. Actually, is it the same numbers? Nope, not quite. 14, no, not quite. So what we would do in this case is find where the first one with children is, 43, happens to be at I equals 4, and then down heap it, down heap, right? And then go to I equals 3, down heap the 13, right? Either compare it to 8 and 11, so it goes there. Then you look at 2. This is a case where you can't just stop if you don't have to do any swapping. If you don't have to swap, you can't just stop in this case. You have to keep going. Okay? This is a loop, by the way. Just a straight up loop from n divided by 2 back up to 1. And then finally we down heap 14, and then we have to down heap that one again, and we're done. Okay? Questions on down heaping? Yes, or heapifying.
Why is the 14 the only one you have to down heap twice?
Why is 14 the only one you have to down heap twice?
Or like, why is the only one you're checking?
I did check the other ones. I just didn't have to do anything with them, as it turns out. Like this one didn't have any children underneath the 13 once I changed it. This one, same thing. It happened to be the first one that really, well, I guess the 9 would have mattered, but it didn't have to actually do anything. It just turns out, it just happened to be that way in this case. Okay. Yeah, maybe I should have picked a better example. Yeah. Okay. All right. All right. So that's how you make a heap, and it's actually kind of cool when you look at it. When you actually do the heap when you actually build heap, it's called, right? Well, it's not a good example because it's not showing me everything, but hang on. All right, it's not quite as mesmerizing as I thought. Hold on. There you go. All right, if I can actually speed this up a little bit, or a lot, but what it's doing is it's just swapping, it's just down heaping everybody in order and going back and doing it. And then you end up with a heap. So relatively straightforward. Okay? All right. So as I said, this week's lab is on heaps. Okay? If you get to the lab and you have no idea what to do, download the slides and look at these slides I'm just about to show you. Okay? You need to implement 3 functions. Build heap, which we just did. All right? Remove, and down heap. You will not have to do up heap. The lab isn't actually checking that. What we're trying to do in the lab is actually we're actually sorting a bunch of strings. Okay? The reminder, the minimum item is at location 1. Don't forget that. Some people forget that, and it ends up messing them up. Okay? Here's some more hints on build heap. Remember, okay, first of all, you'll be given the program itself already puts all the values into the heap for you. All right, it's into a binary tree. Okay, and then all you do for this is you start from position heap size divided by 2, the first with any children, first element with any children, and then call down heap on each element back up to the first. It's just a reverse loop back up to the first. Done. Okay, you have to write down heap too, but you also have to write remove. Removes the minimum item. Again, you're going to use down heap, right? Move the last item to the new empty position, and then down heap that item. And down heap is going to be a recursive call. It's a real simple one. And then finally, you are going to have to do down heap. This is the trickiest one. Okay, you might want to start with it, but it's definitely the trickiest one. Here's the algorithm. Determine if there's a smaller child. Remember, you have to do that first. If there's even any children. If there is, deal with it. Okay, deal with which one. If they both exist, you replace with the smaller child, and then you recurse as you down heap. Okay, not too bad, but if you get confused, go back to this and go, oh, okay, I see what the algorithm is. Okay, questions on that? All right, last thing, I have some. I promised you I'd start putting references and things here. The Wikipedia article on binary heaps is very good. If you just look up heap on Wikipedia, it actually goes to a page that's got more stuff in it than you probably care about. Like it's got other kinds of heaps and stuff. But if you look at binary heap, it's actually a very good article. It talks all about the algorithms and whatever. The visualizations we already showed you. You can go and play around with those. Our textbook, which I don't think I've ever mentioned here, right? Besides like the first day. On page 540 to 545, they've got a description of heaps. It's all right. I mean, I think the Wikipedia article is actually slightly better in this case. But that's the way it goes. Crowdsourced and all. And then if you want more detail about like more of the mathy stuff, there's a video online where I think it's an MIT course that goes into a bunch more detail. They do it with max heaps, so don't get confused. He's going, oh, it's the wrong way. Well, it's max heaps on that one. But that's a video you can watch there. Any questions on heaps or anything else? All right, we'll see you guys in lab or Wednesday.